Hello everyone, this is Dr. Mahender, Associate Professor of Mathematics, Department of Mathematics, B.V. Raju Institute of Technology, Narsapur. The course name is Linear Algebra and Calculus. Today I am going to cover the applications of Heymilton Theorem. So before proceeding to the lecture, so what is the Heymilton Theorem? So once we have the statement, then by using the proof is not there in the syllabus, by using the result of Heymilton Theorem, so we have mainly two applications. So there's generally two kinds of problem they are asking in the question examination. One is the verify Heymilton Theorem. By using Heymilton Theorem, find inverse and power of a matrix. This is the first type of problem. The second type of problem is we can reduce the higher degree polynomial to the lower degree polynomial by using Heymilton Theorem. Now, today's lectures I am going to cover these two types of problem. So first of all I will state what is the Heymilton Theorem. The statement of the theorem is every square matrix satisfies its own characteristic equation. So this is the statement of the Heymilton Theorem. So sometimes short form we will use the CHT also, the abbreviation. This is called Heymilton Theorem. So the statement of the theorem is every square matrix satisfies its own characteristic equation. We know, suppose if you take a 2 by 2 square matrix, by using characteristic equation, we'll get the second degree equation. So if you take A is, for example, A is the 3 by 3 matrix, then the characteristic equation will get the third degree equation. Then by using this theorem, so what we have to verify means every matrix satisfy its own characteristic equation. So first I am going to cover the first type of problem is verification of Heymilton Theorem. By using Heymilton Theorem, how to obtain or how to find inverse and power of the matrix. The first type of problem we'll see first. The first one, verify Heymilton Theorem for the matrix A is equal to the first row 1 2 minus 1 1 2 minus 1, second row 2 1 minus 2, third row 2 minus 2 1. So the verify Heymilton Theorem and hence find A inverse and a to the power of 4 using Heymilton Theorem. So this is the first type of problem. Verification Heymilton Theorem. By using Heymilton Theorem, then how to find inverse and the power of a matrix. So before proceeding to the problem, so we require the characteristic equation of the matrix. So first the statement of the theorem is what Heymilton, every square matrix satisfies its own characteristic equation. So first we have to find characteristic equation of the given matrix. So what we have the formula for that one? The characteristic equation of A is det of A minus lambda equal to 0. So this is the main formula, but we have the shortcut formula for computing the characteristic equation. So for 3 by 3, so we'll get the third degree equation, that is lambda cube minus s1 lambda square plus s2 lambda minus s3 is equal to 0. So this is the better, instead of proceeding with the general equation, if we proceed with this one, we'll get directly required equation. So here what is the S1? The S1 is Here S1 is the trace of the matrix. What is the trace? The sum of the principal diagonal elements. So here 1 plus 1 plus 1 is equal to 3. The S2 is called sum of minors of principal diagonal elements. So find minor of A11, minor of A22, minor of A33. So the minor of A11 is obtained by deleting the first column and first row. We'll get 1 minus 2 minus 2 1. The minor of A22 is obtained by the second row and second column. The second row and second column will get 1 minus 1 2 1. The minor of A33 is obtained by deleting this third row and third column. Now deleting this third row and third column will get 1 2 2 1. Now this is the determinant of 2 by 2 matrix. We know determinant of A, B, C, D. If we have, then how to obtain this one? A, B, C, D. If we have like this, then AD minus BC is the answer of this 2 by 2 determinant of the 2 by 2 matrix. By using this, 1 is 1 minus 4. This is 1 plus 2. This is 1 minus 4. This is minus 3. This is the plus 3 minus 3. The answer is minus 3. Now S2 is so next S3. S3 is what? Determinant of the matrix. We know, we are familiar with the computing determinant of a matrix is the sum of the products of elements of any row or any column with corresponding cofactor. Usually we will take it with respect to first row. If you take it with respect to first row, then you have to keep in mind the signs of the element. This is the plus, minus, plus. So this, right, the 1. Yeah. This minor of this one is what? 1 minus 4. This we have the minus 2. Now deleting this second row and first column. 2 1s is 2 plus 4. The minus 1 minus 2 times minus 2 times minus 2 times 2 is the minus 4 minus 2. So minus 4 minus 2. Now this will simplify. This is the minus 3. This is the 6. 6 times minus 2 is the minus 12. Then this is the minus 6. Minus 6 times minus, then plus 6. Then we'll get, if you're simplifying this one, this is the minus 15. Minus 15 plus 6 will get the minus 9. Now just substituting this after getting this S1, S2, S3 value, by substituting in the given equation, we'll get the required characteristic equation. So this is what? Lambda cube minus 3 lambda square minus 3 lambda plus 9 equal to 0. Lambda cube minus 3 lambda square minus 3 lambda plus 9 is equal to 0. Just as substituted, here S1 we got 3 and S2 we got it here minus 3 and S3 is equal to minus 9 by substituting. So this is the characteristic equation. So what is the statement of the theorem? Verify means what we have to prove. So we have to prove this matrix A satisfy its own characteristic equation. Satisfy its own characteristic equation. Now this is the characteristic equation of the matrix A. This is what? Lambda cube minus 3 lambda square minus 3 lambda plus 9 is equal to 0. Now we have to show that this A satisfies this equation. Means we have to show A cube minus 3A square minus 3a plus 9a is equal to null matrix. We have to prove that one. So once you prove this one, so this theorem is verified, means the matrix A satisfies its own characteristic equation. So for that, what we require? We require a square, we require a cube, we require. Already a we have. Now then compute whatever the values we require for this equation. First we have to compute. Then compute a square. Then how to get a square? A times a. So this we have the a. The a metric is 1, 2, minus 1, 2, 1, minus 2, 2, minus 2, 1. This is a. And a times a is a square. Again, this is nothing but a times a. 1, 2, minus 1, 2, 1, minus 2, 2, minus 2, 1. So we know the multiplications rule. If multiply 2 3 by 3 matrix, the resulting matrix also will get 3 by 3. So we'll get this one, like this. The resulting matrix is this one, this A11, A12, A13, this is A21, A22, A23, A31, A32, A33. So we know how to multiply the two matrices. So the A is a 3 by 3 matrix, and again we are multiplying another 3 by 3 matrix. The resulting matrix also will get 3 by 3. Then how to get the entries of the resulting matrix? Just look at this one. Here A11, the A11 is obtained by the first row is multiplied with the second column of the second matrix. The first row of the first matrix is multiplied with first column of the second matrix. Will get the A11. Then how to get this A12? A12 is this, the one represent row, this the second whatever the number we have that represent for the column. So first row multiply with second column will get the A12. Similarly, we'll get this one. The first row will multiply with third column. We'll get A13. Similarly, A21, second row multiply with first column. A22, second row multiply with second column. A23, second row multiply with. So we'll compute one first. Yeah. So this, look at this one. 1 times 1 is 1. The 2 times 2, 4. Then minus 1 times 2, minus 2. Now A11 is over. A12. The first row multiply with the second column. 1 times 2, 2. 2 times 1, then minus 1 times minus 2. So like A13. Then how to obtain A13? The same. The first row multiply with first column. What is the first row? 1, 2, minus 1 multiply with minus 1, minus 2, 1. So this 1 minus 1 is the minus 1. 2 times minus 2 is the minus 4. Then minus 1 times 1 is the minus 1. So we'll get, so we'll do this one like similarly. Here if you get this one, there's 3 will get. Here we'll get 6. Here we'll get minus 6. Similarly, if you multiply in the same manner, means the second row multiply with the first column. Second row multiply with the first column means what? 2 1s are 2. Then 1 2s are 2. Then 4 minus 4 will get 0. So like that, if you similarly if you proceed, we'll get the remaining entries also. We'll compute all this like 0, 0, 3. In the same manner, if you go like, then we'll get A21, you will get A22 and A23. Like A31, third row multiply with the first column. A32 means third row multiply with the second column. A33 means third row multiply with the third column. So again, we need A cube also. We need A cube also. We need. Then a cube we can obtain like a square into a. Already we have a square, just now we got it. What is the a square? 3, 6, minus 6, 0, 9, minus 6, 0, 0, 3. This is what the a square. Then a we have already this one. A 1, 2, minus 1, 2, 1, minus 2, 2, minus 2, 1. Similarly, if you multiply this 2 matrix, again the resulting also will get the 3 by 3 square matrix. So like A1 first row multiply with first column, the first row multiply with second column, the first row multiply with third column will get the first row of the resulting. Here I will similarly I am directly writing that one. You will compute this 3, you will get this 24. This is the minus 21 will get. Then 6, 21 and minus 24. Even with this one you can do in calculator also. Allowed also 6, minus 6 and 3. So then, so whatever the powers we require, first you have to compute. After that, consider what you have to consider. You have to consider this. You have to consider by taking in place of lambda. You have to take the a. So a cube minus here means nothing but LHS of this one. Okay, a cube minus 3a square minus 3a plus 9a you have to consider. What you have to consider? Consider a cube minus 3a square minus 3a plus 9i. So we have a cube value here, we have a cube, just to substitute here. Whatever we have this one. Minus a square, here you have to write it a square. Again here write it a. This is right, take it as the identity matrix. This will take it as the identity matrix. So this is what 1 0 0 0 1 0 0 0 1. So a we have already 1 2 minus 1 2 1 minus 2, then 2 minus 2 1. So already this is a square, we have that one 3 6 minus 6 0 9 minus 6 0 0 3. So similarly you have to substitute your a cube also here. That is what 3 24 minus 21, the 6 21 minus 24, 6 minus 6 3. Then even if simplify, definitely even if you do also will get this is the 3, this is the minus 9, the plus 9 plus 3 minus 3. Look at this one, definitely will get 0 0 will get it. So 0 0 0. Even examination also, once you complete, even if you write direct also, then no problem. Therefore a cube minus 3a square minus 3a plus 9i is equal to 0. Here not 0, this is the null matrix. Now it is in matrix form. This is a matrix equation. So therefore a satisfying its characteristic equation. What is the characteristic equation? Its characteristic equation is lambda cube minus 3 lambda square minus 3 lambda plus 9. Therefore a satisfying its characteristic equation means hence verified Keyley-Heymilton theorem. So in the problem, the first part we have to finish it. What is the first part? Verify Keyley-Heymilton theorem for the matrix K. After that, what we have to find? By using Keyley-Heymilton theorem, so we have to find inverse and power of the matrix. Then how to find inverse and power of the matrix? By using Keyley-Heymilton theorem. So we will do that one. So next, finding A inverse. Then how to find A inverse? Already we know the general method already we have, but the here intention is by using this theorem, the Keyley-Heymilton theorem, then how to find the inverse of the matrix. But just now we proved A satisfies its characteristic equation by Heymilton theorem. So we have the result. We have A satisfies its characteristic equation. A cube minus 3A square minus 3A plus 9I is equal to null matrix. Where from I am writing this one? Just now we proved, and also we know the statement of the Heymilton theorem by CHT. By Heymilton theorem, every square matrix satisfies its own characteristic equation. Now, in order to get this A inverse, what we have to do is pre-multiply both sides A inverse. Then I am multiplying A inverse. Now, A inverse A cube will get A square will get. Then minus 3 times A inverse A square is A. Minus A inverse A is I. Then 9 A inverse is equal to 0. So we have the property of A inverse if you have, that is 1. And also any matrix I into A will get always A. So these two properties I have used in this one. Now from this our objective is what? To find A inverse. From that find out A inverse. So this is the A inverse is equal to 1 by 9, 1 by minus A square plus 3A plus 3I. So if you have the time, then you by substituting will get the answer by you substituting all these values. So whatever we have that and simplifying will get the A inverse answer. Then if you have time, then you will do it, or else even keep it also. We have considered as the right answer. Already A square we have, A also we have, this I we know. Just simplifying will get this. Just you check it also at home. This is the 3, 0, 3. We'll get this one. 6 minus 3, 0. This is 6 minus 6. You check it at home by verifying this one. So this is A inverse. Then next finding A to the power of 4 by using Heymilton. Someone may ask, then even already we have A cube, by multiplying one more time we'll get A4 now. Here the intention is not that one. Then how to find the inverse, the power of the matrix by using this theorem. So here by Heymilton theorem, already we have A cube minus 3A square minus 3A plus 9I is equal to 0. We know that every square matrix satisfies its own characteristic equation. So in order to get the A power 4, just pre-multiply both sides A. So A, then A times this one. So the A times A cube is A power 4 minus 3A cube minus 3A square. 9A is equal to 0. From this A power 4, write it. A power 4 is equal to 3A cube plus 3A square minus 9A. So already A cube we have, already A square we have already. By just simplifying this, we will get this one. Just to check it also at home. This is the 972 and minus 72. This is 0, 81 minus 72, 0, 0, 9. So hence we proved this problem. Hence we proved the Heymilton theorem, and also we find the inverse and power of the matrix. Here main thing we have to remember is generally, so while we are evaluating of the as an examiner, just we will concentrate first whether he got correct equation or not characteristic equation. So once you get this characteristic equation, the rest of the portion is very simple. Just only thing is what? So whatever the powers we require, just you have to first compute and just substituting and show that satisfying that equation. After that, how to find inverse and power of a matrix by using the result of the theorem. Just pre-multiply both sides A inverse. From that last whatever we have the term A inverse, from that you can get A inverse. Then multiplying Pre-multiplying A by A will get the A power 4. So this is the first part of the problem regarding to the Keyley-Heymilton theorem. The second type of problem we have so we can express a higher degree polynomial to the lower degree polynomial by using Keyley-Heymilton theorem. Now we have finished the first type of problem, the verification of Keyley-Heymilton theorem, and using Keyley-Heymilton theorem, then how to find inverse and power of the matrix. The second type of problem is we can express the higher degree matrix polynomial to the lower degree matrix polynomial by using Keyley-Heymilton theorem. So now we are going to do that type of problem. If A is equal to 2, 1, 1, 0, 1, 0, 1, 1, 2. Then express a to the power of 8 minus 5a to the power of 7 plus 7a to the power of 6 minus 3a power 5 plus a power 4 minus 5a cube plus 8a square minus 2a plus I as second degree quadratic polynomial. By Keyley-Heymilton theorem. So this if A is a 3 by 3 matrix, then this has given that 8th degree matrix polynomial. This 8th degree matrix polynomial to reduce to second degree matrix polynomial by using Keyley-Heymilton theorem. Even sometimes in the question without mentioning also, then just simply you will give the A, just compute this 8th degree polynomial value. So you have to understand that by using Keyley-Heymilton theorem, so we have to solve the problem. Otherwise, will take almost 1 hour to compute this equation. Okay. So what is the statement of this theorem is the Keyley-Heymilton theorem states that every square matrix satisfies its own characteristic equation. So in order to apply the CHT, means Keyley-Heymilton theorem, so we need characteristic equation of this matrix. So first we have to find the characteristic equation. So characteristic equation is determinant of A minus lambda is equal to 0. This is the main formula. But here I am using the shortcut formula lambda cube minus S1 lambda square, then S2 lambda minus S3 is equal to 0. We know what is the S1 here? S1 is the trace of the matrix. So trace means what? Sum of the principal diagonal. So 2 plus 1 plus 2. This is what? What is the S2? The S2 is the sum of minors of principal diagonal elements. What are the minor principal diagonal elements? The elements lie on the principal diagonal is called principal diagonal element. So we have to compute the sum of minors of principal diagonal elements, means we have to compute minor of A11, minor of A22 plus minor of A33. So minor of A11 is obtained by deleting the first row and first column. It's the 1, 0, 1, 2. The minor of the A22 is obtained by second row, deleting the second row and second column will get 2, 1, 1, 2. So minor of A33, third row and third column. This will get 2, 1, 0, 1. So we know this AD minus BC is 2 minus 0 is the 2 will get. Here we will get 4 minus 1 is there, you will get 3. Here you will get 2. Minus 0 is 2. So answer is the 7. Answer is 7. Then S3 is what? S3 is what? Det. Det we know by using sum of products of elements of any row or any column with corresponding cofactors. Then I am using the first row. I will compute the determinant of matrix. So for that we first plus minus plus. So 2 the element, and this minor is what? 2 minus 0 is what? 2 will get. Minus 1, deleting the second row and first column, this 0 you will get. Then 1, this will get 0 minus 1. So this is will get 4 minus 1. 4 minus 1 will get the 3. So therefore, the equation by substituting this S1 value, S2 value. So what is the S1? Is the 5. What is the S2 we got? 7. What is the S3 we got? Determinant 3. So then substituting will get lambda cube S1 minus 5 lambda square plus 7 lambda minus 3 equal to 0. So this is the characteristic equation of the matrix. By Heymilton theorem, we have every square matrix satisfies its own characteristic equation. So therefore we have a cube minus 5a square plus 7a minus 3i is equal to null matrix. So by theorem we have the a cube minus 5a square plus 7a minus 3i is equal to 0. Now using this result I am going to reduce this given 8th degree polynomial to the lower degree polynomial. The best way is doing this because of it is a factor, mean better you divide this 8th degree polynomial by this one, whatever the remainder will get, that is the required answer. So the easiest way I am doing here. So 8, sorry, this is the a power 8 minus 5 a power 7 a power 6 minus 3 a power 5 a power 4 minus 5a cube 8a square minus 2a plus I, because it is a factor. So therefore better you remember divide this one, a cube minus 5a square plus 7a minus 3i. Now here a cube, here a power 8. So multiplying with what you will get? A power 5 you will get this one. Now a power 5 times a cube, a power 8 minus 5a to the power of 7 a power 6 minus 3 a power 5. Multiplying a power 5 by this will get this one. Then this is a minus, plus, this will get cancelled. So here write it a power 4 minus 5a cube plus 8a square minus 2a plus I. So next what times you take it? Here a cube we have, here a power 4 we have, then we'll go with a. So multiply with a, this one will get a power 4 minus 5a cube plus 7a square minus 3a. Now subtract this one, minus, plus, minus, plus. So we'll get this cancel. This is 8a square plus a plus I. Therefore, this is the required answer. So this 8th degree polynomial we can express the second degree polynomial by using Heymilton theorem. So instead of computing this 8th degree expression, just if you compute this one, will get it is similar to this one. So here by using Heymilton theorem, we reduce the 8th degree polynomial to the second degree polynomial. So similarly, we can do some more problems related to this one. So we'll give one problem, you will try at home. This as a homework, just to do it home this one. If A equal to 1, 4, 2, 3, then express A power 5 minus 4 A power 4 minus 7 A cube plus 11 A square minus A minus 10I as a linear polynomial. By using Heymilton theorem. So we will do one problem as a homework. So similarly, so first what we have to do is, so first to compute the characteristic equation. So by using Heymilton theorem, that A satisfies that equation. So divide that one by with the given polynomial, the remainder automatically will get the linear polynomial, first degree polynomial we get. So hope you understand. So the two types of problems we have Heymilton theorem. The first type of problem is what? Verification and using Heymilton theorem, finding inverse and power of a matrix. The second type of problems are, so by reducing higher degree matrix polynomial to the lower degree matrix polynomial by using Heymilton theorem. So thank you. I am ending the section.
Like, share and subscribe. Hit the bell icon for more updates.